Thank you, everybody, for joining us. Today, as Kevin mentioned, we're going to go over the fundamentals of inverters in general, variable frequency drives, and then we'll kind of tailor in. We'll show some of our displays here. We won't be running anything today. Tune in next week for that one, but we'll just show the two Invertech products that we have here, the E3 and the P2. But we'll go ahead and get started on the basics right now. So for what we're going to go over today, as I said, we're going to go over what is a VFD, what does it do, where and when are they used, what do they replace as far as the technology goes for being able to control a motor. And then we'll go into the applications for a VFD. And then, as I said, we'll go over the E3 and the P2 product. So first we'll start is what is a VFD? So what VFD stands for is variable frequency drive. So what it does, it takes your input power, it goes through multiple different circuits inside the drive itself and powers the motor. The easiest way to describe that and put that in simple terms, it's a motor controller. So you put the input power on one side, the inverter takes that power, makes the power more controllable, and the motor is now able to run at precise speeds, accelerate and decelerate at precise times and predetermined times based on the application, and a whole array of other different customizable functions. Whereas without a VFD, you're just going to turn power on and that motor is running at its full speed all the time. So you get that more control than you can ever have without a VFD. So that's the main definition of a VFD. There are other types of motor controllers. So we have motor starters, where, as I said, it's just basically an on-off switch. As soon as power is turned on to the motor, it's full speed. So if a motor is rated for 1750 RPM, it goes right to 1750 as soon as it's powered up. Now, some of them are dual speed. So the way they're wired in, it'll run at half speed, 3/4 speed, however they're set up. And they have some that are reversing. So you can go up to them, take a switch, and they reverse. Now, there's no slowing down that. There's no adjusting that as easy as it is on a VFD. So again, the VFD allows you to go up to that, control it, fine tune it for what you're trying to do with your application. Then there's even soft starter. So with a soft starter, it applies that slow ramp. So instead of going from 0 to 100% speed, it goes up nice and slow. So that works great, but a lot of times you need it slower than that. Sometimes you need it faster than that. And there's no customizability there. You have to change that physical component right here, has to be changed for you to be able to get that level of control. So that's why you would use a VFD. So speaking of why you would use a VFD, so as I said, soft starting, we kind of group them together. So process control. So you want to control how your motor is ran. So soft starting is one. Speed adjustment. So whether if you want it to be 1750 RPM or 1745 RPM, you have that fine level of adjustment. Whereas without a VFD, you just can't do that. Full system integration, meaning you can tie that into a PLC network. You can tie it into a whole control scheme. So all different VFDs are talking to each other and controlling that application throughout all aspects. So it definitely makes it much more controlled than you ever had without a VFD. Then on the other side, you have protection. So you want to be able to protect the application that you're running. So you want to protect the motor, you want to protect the reducer in our case, and you want to protect the overall application. So you want to make sure that the motor doesn't start too fast. You don't want it to hit the load. You don't want it to overwork itself and fail prematurely. So having that level of protection inside one of these drives definitely makes it safer to use. So an example of that protection is just strictly looking at the amps. So if the VFD is powering the motor, everything's running good, and it's always looking at the amount of amps going to that motor is pulling, I should say. So if that level of amps starts exceeding the rating of the drive or of the motor, it's going to tell the motor to stop running. It's going to pull back and say, hey, something's wrong. It's going to trigger an alarm. It's going to trigger a fault code. And depending on how you set it up and how it's wired into your system, if you will, it'll stop that motor. It'll protect that motor from burning up. So just an example there, but it does many different things like that to be able to protect everything that is wired to that drive. So control and protection, as I said, but there are some alternatives to that before VFDs were around. So for control, you have a chain and sprocket. How do you change the speed? You go up and you change your different ratios on your sprockets. We talked about that in our previous lesson. You change your driven sprocket to your driver sprocket and you get a different output speed. Now that's still an option here. You can still do that. But again, you have to go to the drive. You have to fully shut down the operation. You got to pull the chain off, pull the sprockets off. It's labor intensive, takes time. Still an option, but it just takes some time versus a VFD, you just walk up to it and you can turn it. And same deal with the belt drive. You change your belt drive ratio, you change your belt center distance, you change your pulleys on each side, and you're changing the speed. Now, same thing, you have to shut it down to be able to change it. And then from the protection standpoint, you have torque limiting couplings. So these couplings would go in between the motor and the reducer, or the reducer and the application, depending on how you wanted to do it. But with there, if that exceeds a certain amount of torque, that coupling breaks away and it protects the drive. Now, with that, if you want to change that torque value, you have to change the physical coupling. And we all know that's not very easy to do. With the VFD, you go in, you're changing a setting, and within minutes, you're adjusting where it'll shut off and where it'll fault out. So much easier to do. And then on the bigger picture, more recently, is a whole bunch of sensors. So you can do tension sensors, or in some cases, pressure or vibration, things like that. But some of these complex systems, sensors are all over the place. You'd have millions of wires running everywhere. You'd never be able to get ahead of it. The VFD does a good number of that all by itself. So it's a standalone item that can help protect your application 100%. So just some terms when it comes to VFDs, the buzzwords, if you will, when you're selecting one or when you're looking at one. The first one we get a lot of questions about is enclosure rating. So what the rating is referring to is the ingress protection of the physical box around the inverter itself. So it's your IP rating. So IP20, IP55, IP66. The higher the number, the better rating it has. So IP20, they're designed for what we would call decentralized control. So they're mounted inside a panel. So when they're in a panel, water can't get to them. Dust is very limited because it's completely sealed. Whereas with an IP66, that IP66 is more of a standalone. It can be mounted right on the side of the conveyor. It can get wet. It can get dusty because it's fully sealed. So that kind of comes in depending on your application, where it's mounted, where it's going to be running, things like that. So that is a big selection point there. I mentioned centralized versus decentralized. But the main difference there is where the drive is mounted. So decentralized is there's going to be one drive and one motor way out, say, on the conveyor, if you will. So there's going to be one conveyor, one VFD, one motor. And then there's another conveyor somewhere else. There'll be another one. It'll be physically right there. So it's in a smaller cabinet. It's at usually, I'm sorry, I misspoke. There'll be the IP20s where the decentralized would be. I'm sorry about that. But decentralized, all the wires are out there, less wires from the VFD to the motor because it's all located right there. Whereas centralized, there'll be a room full of VFDs, nowhere near the application in some cases, hundreds of feet away. And all the VFDs are in a big cabinet or in a big control room. And you have to do more wiring and things like that. So the trend now is more decentralized, but centralized is still out there as well. And there's just kind of the difference between the two. So on the left there is IP20, and on the right there is IP55 specifically. But you can see it's more covered. There's more protection for the components inside. As you know, water and electricity do not mix. So you definitely want to keep water out of these drives. So that's where that comes in. And then there's the frame size. So we have frame sizes on our reducers. It's the same concept. The frame size is the physical size of the VFD itself. So the drives we have here are sizes 1, so they're the smaller ones. But if you go sizes 2 or 3, 4, et cetera, they get larger and larger. Now, manufacturers do it differently, but our Invertex here are sized 1, 2, 3, et cetera, as they get. So the bigger the number, the physical size of the drive itself gets bigger. Now, one thing as far as selection I wanted to mention, we get this question a lot too. What is the relationship between the motor selection and the drive itself? So the main connection there is amps. So these are sized based on amps. So if your motor is rated for a full load amp rating of 5 amps, you want to pick a VFD that's 5.1 amps or higher. Anything less than that, the drive is not going to, it'll run it, but it'll trip out and you risk damaging the drive. So that's the main selection criteria you use for selecting a drive. Once you have the amps, make sure your amps are covered. You can look into the options, your configurations, your I/O, your input outputs, things like that. But the amps is the critical selection point when you're selecting a VFD. So here's the frame sizes here. They get bigger as the frame size gets up. Now that goes with horsepowers. The larger the horsepower is usually the larger the frame size. Now, some typical VFD applications, the simplest example we can go over is fans and pumps. So the way they work in these applications, you have a fan, you have your VSD or variable frequency drive or variable speed drive in this case, but variable frequency drive, same concept. You're going to control that motor, which is controlling a fan. Now, with the airflow going through here, with the addition of a VFD, you can add a sensor in the flow of the air, and that sensor feeds back a signal to the frequency drive. Now, with that frequency drive can adjust the speed of the motor to get the right airflow that you're looking for in your application. Now, when I say airflow, that can be water flow, pump, conveyor speed, whatever the case may be. It can use other sensor inputs to regulate the speed, whereas without a VFD, you just can't do that. So that's one example. And another one is conveyors. So we run into that a lot. That's one of our biggest install bases is conveyors. Now, with conveyors, you have a lot of different things going on. Certain times of day, you'll have variable speed. So in the beginning of the day, you want to run motor speed of 1800 RPM, but at the end of the day, you might want to run 1200 RPM, depending on the load, depending on number of packages, number of baggage, whatever the case may be. You have to change that. So with the VFD, you can have it programmed to change based on time of day in some cases. And as I mentioned, the centralized control. Here's an example here of airport baggage. You have, in this picture alone, we have 1, 2, 3, 4 reducers. Each one of those are going to have their own drive, and those are probably centrally located, and they can adjust them from there via the network or walk up to them and adjust them. So you just get that level of protection and control that you don't have without a VFD. So next, we'll switch over to the products. Before I do that, do we have any questions up until now, Carla?
We do not have any questions yet.
All righty. All right, so we'll go ahead and keep going then. Feel free to jump in with any questions. So for the Invertech, as Kevin mentioned, we're gonna, based on our product line and the complementary products for our gearboxes, we're gonna stick to the E3 and the P2, although Invertech has a full line. As you see, they have multiple different sizes and different features for different applications, but we're gonna stick to the E3 and the P2. So we'll start with the E3. So with E3, the E in E3 is economy. So meaning it's the simpler of the two drives. It has less features, but still very feature rich. You can do a lot of different things with this drive. 3 is just the 3rd generation. Very easy to use, very easy to program. And we'll be programming them next week. So we'll have the software open and we'll go through the programming process. But in general, very easy to use. They're very small, as you can see, but powerful right there. That's a 1 horsepower drive on our display right there. And from a selection standpoint for the IP20, the smaller sizes, the smaller frame size, or the smaller enclosure, I should say, we're up to 50 horsepower. Now, again, this is all dependent on your voltage requirements. But in most cases, we're up to 50 horsepower on the IP20 and up to 30 horsepower on the IP66. So we definitely have plenty of options available. Now, if we take a closer look at the IP20 that we have on display here. So a few different features that they have. Obviously a very eligible readout there. This is the P2, but this is the E3. We'll stick to this one for right now. Easy to use motor terminals, very easy to access, wide open connections. They're even protected for safety as well, but you can easily wire them up to wire the motor. One of the features I like big time is this reference card that's right on top here. You won't be able to see that on camera, but that shows the basic parameters to program the drive. So it's a nice quick reference card. You don't have to search for the manual. It's essentially right on the unit for the basic programming of the drive. As a standard, from a network communication side, they come with Modbus and CAN open as a standard, but we can definitely change those on the larger ones, but as a standard, that is available. So the smaller frame sizes are DIN rail mountable. It may be hard to see here, but we'll switch back to the slides here and you can see where that is. But they're DIN rail mountable on the smaller frames. So you can see much easier to install, and they still have the keyhole mounting on the top for quick panel mounting if you prefer that way. And the connections for the OptiStick, we'll go over that here in a little bit for the options, but the OptiStick is a nice rapid programming tool, and that plugs into that RJ45 port right on the front. So we switch over to the IP66 version of the E3. Little different, as you can see. much bigger. This is where the protection comes in. The main differences here, still the same functionality inside, but outside you have local speed adjustment here with this speed knob. You have motor direction you can change right on front. And there's even an option for a disconnect out here. So this is a motor disconnect. So this would come in handy for if the user needs to take a look at the motor, and then from afar, he can look back at the drive and see if the motor has power or not. So it's a good handy tool to have there. And also on this specific frame size, we have an option for Ethernet IP. Because it's physically larger, we can fit an Ethernet IP card in here and be able to communicate to different piece of equipment via Ethernet IP. So on the IP66 version only, that is available on the E3. With the E3 itself, we can control many different motor designs. So the ones we're used to for all these years are standard induction motors, IE2, IE3, we're good there, but we can also do the newer technology, permanent magnet, as well as brushless DC, all without changing the drive. One standard drive you just change one parameter telling it what motor you're running and a few associating parameters, but it'll run it without changing anything else on the drive. It's still physically the same drive. Some of the built-in application modes, they call them macros, or call them application modes built into the drives themselves. So what these are predetermined parameter sets, if you will, that turn on or turn off certain functionality inside the drive based on what the drive is doing. So as a default, they come in this industrial mode, which is mainly for conveyors and mixers. Now for our applications, that's majority of what we'll be using, but just as a few examples, there's a pump mode, there's a fan mode, and even a fire mode. So pump mode, for example, it knows it's running a pump, so it's going to look out for cavitation speeds. It's going to make sure the motor doesn't get hurt when certain pressures get with different pressure inputs and such. It's going to watch all that type of thing. Same thing with fan mode. It won't let the motor start if the fan is going in the wrong direction from wind blowing through it or what have you. So it knows, the VFD knows what application it's on, so it knows what to look for in these specific applications. As I mentioned before, a VFD is used for protection, for motor protection. So with these VFDs, it's always looking at the current. So the current going through the motor based on the time, how long that current has been at that level, it'll trigger a fault in the drive. It'll protect that motor from burning itself up. But you can also monitor temperature with a thermistor. So a thermistor would be pre-installed on the motor, and that signal goes to the VFD, and the VFD knows exactly what temperature is inside the windings of that motor. So there's an optional for that as well. And dynamic braking resistors, that's another option, somewhat unique to Invertech, in that you can mount them right on the device itself. So on the smaller, I'll stand up here in a minute and show this, but on the smaller frame sizes, so this is a size 2 and smaller here. So on those, you can actually physically mount the dynamic braking resistor right in the device itself. So we'll show the one picture there, but as I go over here, right on the bottom here, there will be a little slot that you can slide the dynamic braking resistor right in, and then you wire it right up to the correct ports. Now, that's unique, and now it's unique to Invertech. It's not very common in some of our applications because of the loading. You would require a braking resistor that's much larger than that can handle an onboard one, but for some of those lighter duty applications, can definitely be a good feature where it's right in on the drive versus mounted externally inside the cabinet or what have you. So for the network connections, I mentioned it's Modbus and CAN open for the E3 with optional Ethernet IP for the IP66 version. But the big point here is that we can connect to up to 63 drives on either one of these networks. Anything over that, you start getting some disconnect issues, communication issues, things like that. So, but 63 drives on one network is very flexible with some of these larger installs. All right, so the P2 is next. Any questions on the E3 before I continue?
We don't have any questions in the box.
All righty. So with the P2, before we jump into too much, we'll just show a quick comparison between the two. So I'll switch over, I'll stand in front of our little demo again there. And what we have, so this is the E3, as I said, and this is the P2. Now, the main differences that you can see, so on this display, there's a slightly different display on this one. This one has a full readout versus just a segmented display here. This is just an optional display for the P2. But that is a difference. You can get this same display on the P2 as well, But the main difference here is this removable terminal strip. This strip is not removable on the E3, whereas it is here. And also as an option on the P2 is this expansion port. So if I come here and pop open this port, you can see it's a little cover, and in there is where you can add on some additional cards for different options, which I'll cover here in a second. But that's where that goes, whereas the E3 does not have that expansion port. So otherwise, the buttons are the same. Functionality is very similar. The P2 is just a little bit more capable as far as some options. So we'll go over those options right now. So P2, so P in P2 stands for performance. So as I said, it has many more different features. The capabilities are much higher than the E3. 2 is second generation. So they're constantly updating these. So we have the second generation available right now. Still just as easy to use. From the selection standpoint, a little bit broader range in the P2. For IP20, we go up to 350 horsepower, whereas the IP55 and the 66 kind of a slightly different range, 55, 7.5 to 200 horsepower. With the 66, we can go up to 15 horsepower. So again, that all depends on the voltage requirements, both input and output, but pretty broad range is covered there. So the IP20, very similar. We'll go back over there real quick. Now, since this one has the newer display on it, it doesn't have this card. If it had this segmented display on the P2, it would have the same card, so that's available too. Same DIN rail mountable. You can use the same OptiStick with the RJ45 port right here. With this version, if I go ahead and hit the parameters here, you can see what the parameters are, so you don't necessarily need this quick readout. All the display is right there. So very easy to use, very nice display on there, and same terminals, quick access terminals, both input and output. So very easy to connect. Same Modbus can open as well as a standard, but I'll cover those options here in a minute. We have a few more than just those. So, but Modbus and can open come as standard, just as on the E3 as well. So on the IP55 version, very similar, same options internally. Obviously, it's the same drive internally. The display is very similar, a little bit of a full readout, multiple languages, things like that. But with the larger one, there's 2 RJ45s inside there, just because it's physically a larger drive, so you have a little bit more room for some connectors in there. But same control terminals are all covered here. It's just obviously with the IP55, you want some more protection. So, but same features otherwise. Now you've seen this slide before because it's the same for the P2. They can definitely run all in motor types, as we said before, all with the same drive. We don't have to change to a special drive to run any of these motor types. So induction, permanent magnet, or even brushless. So definitely a definitely flexible drive. Extensive I/O. So as a standard, I'll put all these up here. There's a lot of them, I know. I'm not going to read through them all, but as a standard on the P2, there's 5 inputs, 4 outputs. And with that, I kind of covered already with the expansion port there, but as a standard, it's 5 out, 5 in, 4 out. But if you need more than that for whatever reason, you use this expansion port that I showed you earlier, and you can add more. So up to 3 more in some cases. And there's other ways to use external mounted cards using some other features that I'll go over here in a second, but there's very flexible depending on your application. We could add a whole bunch of different inputs and outputs and different relay outputs and things like that. So it makes it very flexible for many different systems. Now, some of the advanced networks. So there's an example of one of the expansion cards. Now with that, as I said, Modbus can't open as standard, but using that expansion port, we can connect to any of these other different communication protocols. So just by changing that plug, if you will, on the bottom of that card, and going into that parameter and telling it what language you'd like it to talk to, what module you're plugging in, you can cover all these languages here. So again, it makes it very flexible. Now, a very unique feature to Invertech into this P2 specifically is an integral function block editor. So also sometimes referred to as a PLC, kind of similar. But what it is it's a built-in PLC essentially that you can program to do any number of things. You can have it, here, just some examples here, but you can have it use the inputs that are previously programmed or wired into it, and you can have it do math, you can have it timers, you can have it compare different data at different points and control the drive based on that. You can have it change the display to say good condition to whatever you want it to say. So it definitely makes it even more flexible than any other VFD itself. It's built into it. It uses its own logic to control the motor based on the inputs it's seeing, and you can run it from there. And we'll definitely go over this next week. So make sure you tune in next week, and we'll go over those specific options with that function block editor. Now, some of the options, we have some of them right here. So this is the OptiStick right here. It's real small. I don't know if you can kind of see how small it is compared to my hand there. But it's kind of the size of a flash drive. You just take the cover off and you plug it right into the RJ45 port. And with that, it allows you to rapid prototyping. So if you have one drive set and you have, say, 50 more to go for whatever your application is, you plug that in, you download using there's touch buttons on the front that'll light up once you plug it in. You download that parameter set to the OptiStick. And once it's done downloaded, you just pull it out, walk to the next one, and you hit the upload button on the next one. And you can just keep going down the line. So if they're all doing the same thing, all that can be programmed within a matter of minutes instead of going to each individual parameter. Very useful tool. And you can even connect it to your smartphone via Bluetooth. And you could use the mobile OptiTools Studio software and be able to do all those features with that, all with your phone as well. You can control the drive, you can monitor the drive, things like that. So very, very useful tool. Now, the other option here is the wired version. So this uses USB stick. And this goes to the RJ45 that's on the front of the device as well. But the only difference between this and the OptiStick is that you have to use a laptop because it's wired. But once you have that, you could use the software for programming, monitoring, using the PLC function specifically on the P2. It's just a very flexible option. And I've used it a lot in programming some of these drives. So definitely a very useful tool. Now, some of the other options, these are kind of standard industry standard options, if you will, but remote displays. So if these are cabinet mounted and you want to display this panel on the front of the cabinet without having to open the enclosure, those options are available. They just plug into the RJ45 up front and they just duplicate the controls to the front of the display, front of the cabinet, I should say. And also we can do the network connections as well. So these aren't nothing special about them, but if you need a one-stop shop, we definitely have them available. So we can definitely get you set up for a large network of multiple drives. So that's all I had on the P2 and A3. Is there any questions on the P2?
We do not have, well, I guess we consider this a question. Do you recommend line and load reactor or filters with these VFDs?
That kind of depends on your application. If you're running, majority of our applications that we're used to, the VFD is relatively close to the motor itself. So anything over 100 feet, I would probably consider it as an option. But anything less than that, you probably don't need it unless you know you have bad supply power, bad line power coming in. If it's a bad signal, I would recommend it. But we do have them available if you feel you need it. Absolutely.
I think we have a few general questions. Oh, wait, one just came in the box. Excuse me. Can VFDs have separate brake connection option with the same enclosure?
Separate brake connection. Are you referring to the dynamic braking resistor, or are you talking about controlling an external brake?
Oh, I will wait for them to clarify.
Clarification on that. In regards to an external brake, the P2 does have a circuit to control an external brake, as far not the high voltage side, but it controls the relay. It can tell the brake when to activate. And again, that's another advantage of using a VFD, because you're getting that timing correct. Because you don't have the VFD, if you have a VFD powering the motor and the brake is still applied because the VFD doesn't know it, you're going to try powering through a brake and it's never going to end well. So tying the brake back into the VFD, the mechanical brake on the motor, is definitely a good feature.
Yes, they were talking about the external brake.
External brake. Okay, yeah. These do have a circuit for powering and controlling an external brake using one of the relay outputs. Yes, they do.
All right, we have another question. Why do we need a dynamic brake resistor?
That's a tough one to explain. It's mainly for applications that the term is floating the load. So how can the best way to explain it? So if you have an incline conveyor and you have a load on that conveyor. When, say, the motor is running and all of a sudden gravity takes over, and now the motor is being pushed, if you will, from the weight of the load. Now what happens is that essentially turns the motor, it's spinning at its speed that the VFD is telling it to spin at, but the motor is now being sped by an internal force, gravity, and that turns the motor into a generator, and that energy has to go somewhere. If you don't have a dynamic braking resistor in the circuit, you can burn up the motor, you can burn up the VFD, because all that energy is coming somewhere. It'll turn into heat. There's a lot of bad things can happen. So it depends on the application, when and if you need them. But if there's any situation where the load is making the motor spin faster than the VFD is telling it to spin, you need one, because it's going to turn the motor into a generator, and that energy has to go somewhere.
All right, we got quite a few, so I'm going to keep going. Can we use the E3 for lifted applications and industrial uses?
Usually with by lifts, I'm assuming you mean cranes or hoists or things like that. You probably don't want to use an E3 on that, just from the options that it has. The P2 has a specific crane and hoist mode. It's made for those type of applications. It looks at different things. So for craning and hoisting, you'd want to use the P2. In general, selection wise, when you come to us and you tell us, okay, which drive would be the best, we're going to start with an E3 until the options, but until we go through your spec. If you tell us, okay, we need Ethernet IP, but we don't need an IP66, well, then we're going to go to P2. But if you're using an E3 for just a simple motor controller, you're just running the load, there's no on and off, there's no speed change, there's no coasting the load or anything like that, we'll go to an E3. So, but a P2 is much better for a crane and hoist.
All right. What communication protocols are most popular? Ethernet IP, Modbus, and does one perform better than the other? Oh, that's a good one.
That is a good one. That's a huge debate in the communication world, which one's better. In my little experience with them, I've dealt with them just enough to be dangerous. They all essentially do the same thing. They just don't talk to each other. So, but I will say the most popular right now, especially in North America, is either Ethernet IP or Profinet. So that's your Allen Bradleys with Ethernet IP, and your Profinet would be your Siemens systems. But do they perform the same functions? I would say yes, absolutely. They just don't talk to each other, and it's just a matter of user preference, which one they want to use.
And the last question, unless someone submits some more, could you clarify what I/O stands for?
I/O, so that's input and output. So there's on VFDs in general, not just these, all VFDs, there's a certain number of inputs and outputs. So inputs can be either digital inputs or analog inputs. Digital means the signal coming in is just an on or an off. So if the digital input is open, it means it's off. If a digital input is closed, it means it's on. That's it. So it just uses, the VFD uses that, say, a start button. So if you have the start button pressed, that signal is now closed, that digital input is now closed, the drive knows to run. When you open that up, it says, okay, it's not closed anymore, we're going to stop. Now, analog inputs or outputs, they can be either one. Analog signals are ever changing. They're usually a range. So it's either 4 to 20 milliamps, 0 to 10 volts, some cases 0 to 5 volts, depending on the system. But what that is it's a changing signal. So say a temperature sensor or a pressure sensor going into the VFD. When the pressure goes up and down, that voltage signal, or amperage in the case of 4 to 20 milliamps, that signal changes, and that's an analog. So digital is just on off, analog changes up and down. So I/O is that type of input and output for the drive. And all drives usually have a set number of inputs and outputs. So depending on your application, you may need an external card or a different quantity of cards or whatever the case may be. But that's what I/O means. It's inputs and outputs.
All right, the question and answer box is empty unless anyone has anything else.
Well, Carlos, thank you very much for moderating. Adam, thank you a ton for taking us through this presentation, answering the questions as succinctly as you did. I want to take this time to remind everyone that, again, we're extremely appreciative of you taking time out of your busy day to join us for this first part of a two-part presentation that we'll be doing where we're doing VFD fundamentals. Next week, we will be resuming this series and actually finalizing it for part two, where we will go through the process of using the OptiTools Studio to go through the programming process and actually see the functionality of the drives themselves. Super excited to have you all back there. We're going to hang out for a little while here in case anyone does have any questions that come up in between now and the next 5 minutes or so that you'll want to ask. But we're looking forward to seeing you all next week. There will be a link that go out for those of you that didn't get an opportunity to register for next week's session. We'll send another out just so you get that opportunity. If you found this information to be beneficial, we'll make this content available to go back for replay. And we encourage you to invite your counterparts or your comrades to join next week if you feel like there'll be some information to benefit there. Thanks again to you, Adam. Appreciate all the help. We hope you all have a great and safe day. And we hope that we can help you be the solution or solve a problem in your specific plan. Thanks again, and we'll see you all next week.
All right. Thank you very much, Kevin. See everybody next week.
Hey, Adam, are you still here?
I am still here.
All right, we got a question that just came through.
Sure.
It says, I took motor control some time back ago, and I remember discussion about vector drives allowing maximum torque capacity at startup. Is it applicable for VFD drives?
Yes. So these VFDs are vector controlled drives. So they have the capability to do that. Absolutely. And so on the P2 specifically, for crane and hoist applications, they can do 200% torque at full load at zero speed. So talking about vector control, that's the best way you can do that. For a crane, you definitely have to have that functionality. So the P2 can definitely do that. Absolutely.
Thank you. And we'll be here for a few more minutes. If anyone else has any questions, feel free to chat, to type them in the box, and I will let Adam know. All right, we'd have another question. Is there any improvement in harmonics, or is a VFD cable to the motor still recommended?
Did you say cable to the motor?
Yes, is
VFD
there
cable?
a VF?
Yeah,
cable?
you definitely want to make sure you pick the correct cable. Harmonics are always a concern. These drives, they are designed to, they know they're going to be there, so they are designed to filter them out somewhat. But definitely making sure you pick the right cable for your application is definitely key. Absolutely.
Thank you.
And just to expand on that a little bit, the length of cable, the length of run from the VFD to the motor is where that takes into account. So as I mentioned before, anything less than 100 feet, you probably won't ever run into it. So consider that an option as well.
All right, well, we're about down to our last minute. If you have any additional questions, you can reach out to your local sales rep that's located on our website,